Can you recall? How is covalent bond formed between two atoms? Consider two covalently bonded atoms, Q and R, where R is more electronegative than Q. Will this atom share the electron pair equally between them? Represent the above polar covalent bond charge Q and R using fractional charge delta plus and delta minus. We learned earlier that covalent bond between two atoms differing in their electronegativity is polar covalent bond. For example, the covalent bond between carbon and more electronegative chlorine is a polar covalent bond. When an organic molecule has a polar covalent bond in its structure, polarity is induced in adjacent carbon single bond too. This is called inductive effect. Consider for example the chloroethane molecule CH3CH2Cl. In this molecule, a positive polarity is developed on C2 by inductive effect of the chlorine atom bonded to C1. Normally, the C2-C1 bond would not be expected to be polar, as it is a covalent bond between the two atoms of the same element carbon. Yet this bond acquires some polarity because of the presence of chlorine atom in the molecule. Chlorine being more electronegative than carbon, the C1 and Cl bond is a polar covalent bond with partial negative charge on chlorine and equal amount of partial positive charge on C1. As the C1 is further bonded to C2, the positive polarity of C1 pulls the shared pair of electrons of the C2-C1 bond more towards itself. As a result, a part of partial positive charge produced on C1 is transferred to C2. This results in developing a still smaller positive charge on C2. In other words, the electron density gets displaced towards the chlorine atom, not only along the C1 and chlorine bond, but also along the C2 and C1 bond. Due to the inductive effect of chlorine, this represents as CH3CH2Cl. The arrow head put in the center of the bond is used to represent the inductive effect. The direction of the arrowhead indicates the direction of the permanent electron displacements taken place along the sigma bond in the ground state. Inductive effect of an influencing groups is transferred to subsequent carbon atoms along the chain of carbon-carbon bond as it decreases rapidly as the number of intervening carbon-carbon bond increases and it becomes negligibly small beyond 3 bonds. This can be represented as CH3CH2CH2CH2Cl delta 3 plus smaller than delta 2 plus smaller than delta 1 plus. The direction of the inductive effect of a bonded groups depend on the direction of the inductive effect of a bonded group depend upon whether electron density of the bond is withdrawn from the bonded carbon or donated by the bonded carbon. According to this ability, the group substituents are classified as either electron withdrawing, accepting, or electron donating releasing group with respect to hydrogen. In the above example, electron displacement takes place towards chlorine. This means that chlorine withdrawn electron density from the carbon chain and is electron withdrawing. Chlorine is said to exert an electron withdrawing inductive effect or negative inductive effect -I effect on the carbon chain. Some other groups having -I effects, negative inductive effects are NO2 nitro, CN cyano, COH carboxy, COOR ester, OR aryl oxy. On the other hand, alkyl groups CH3, CH2, CH3 are considered as groups exerting electron releasing inductive effect, thus inductive effect on the carbon chain. Consider the following molecules and answer the question. CH3, CH2, CH2Cl, CH3, CH2, CH2 bromine, CH3, CH2, CH2R. What type of inductive effect is expected to operate in this molecule? Identify the molecule from these three having the strongest and the weakest inductive effect. The group responsible for inductive effect in these molecules are chlorine, bromine, iodine respectively. All these are halogen atoms which are more electronegative than carbon and therefore all of them exert negative inductive effect, that is electron withdrawing inductive effect. The electron, the negative electron inductive effect of halogens is due to their electronegativity. A decreased order of electronegativity in this halogen follow chlorine more than bromine, more than iodine. Therefore, the strongest negative electroinductive effects is expected in CH3, CH2, CH2Cl, while the weakest negative inductive effects expected for CH3, CH2, CH2I. Which of the CH3, CHCl2, that is ethyl fluoro and CH3, CH2Cl is expected to have stronger negative inductive effect? The group exerting negative inductive effect in CH3CH2Cl is 1 chlorine, while in CH3CHCl2 there are 2 chlorine atoms. Therefore, CH3CHCl2 is expected to have strong negative inductive effect. Resonance structures. Resonance structures. Draw a bond line structure of benzene C6H6. How many CC and C double bond C bonds are there in these structures? Write down the expected value of the bond length of the carbon-carbon bond in benzenes. The cyclic structure of benzene incorporating the 3 alternating C-C carbon-carbon single bond and carbon double bond implies 2 distant bond lengths of 154 picometer and 133 picometer respectively. Refer to table 5.2 and see figure 15.10. Experimental measurements show that benzene has a regular hexagonal shapes and all the 6 carbon bond have the same bond length of 138 picometer, which is intermediate between carbon-carbon single bond and carbon-carbon double bond. This means that all the 6 carbon-carbon bond in benzene are equivalent and are what appear from single Lewis structure. Benzene expectation 133 picometer, 154 picometer, observation 138 picometer, 2 different bond length, observation all bond length equal. Structure of benzene. Can you tell? Write down 2 Lewis structure for ozone. How are these 2 Lewis structure related to each other? What are these 2 Lewis structure called? What Lewis structure of a compound has 2 or more multiple bonds alternating with single bond is called a conjugated system of pi bond. In such a system or in species having an atom carrying p orbital attached to a multiple bond, resonance theory is applicable. We understand the following point from the resonance theory. The pi electron is conjugated and system of pi bond are not localized to a particular pi bond. For a compound having a conjugated system of pi bond or similar other system, 2 or more Lewis structure are written by showing movement of pi electron, that is delocalization of pi electron using curved arrow. The Lewis structures so generated are linked by double-headed arrows and are called resonance structure or contributing structure or canonical structure of the species. Thus, 2 resonance structure can be drawn for benzene by delocalizing or shifting the pi electrons. The position of the carbon atom in the conjugated system of pi bond remain unchanged, but the position of pi electron are different in different resonance structure. For example, in the resonance structure 1 of benzene, there is a single bond between C1 and C2, while in the resonance structure 2 there is a double bond between C1 and C2. Fourth point, any resonance structure is hypothetically and does not by itself represent any real molecule and can explain all the property of the compound. The real molecule has, however, character of all the resonance structure. Those can be written. The real or actual molecule is said to be the resonance hybrid of all the resonance structure. For example, an actual benzene molecule is a resonance hybrid of the structure 1 and 2 and exhibit character of both these structure. Its approximately representation can be shown as a dotted circles inscribed in a regular hexagon. Thus, each carbon-carbon bond in benzene and has a single as well as double bond character, and the ring has a regular hexagonal shape. Resonance hybrid of structure 1 and 2. Fifth point. Hypothetical energy of an individual resonance structure can be calculated using bond energy value. The energy of actual molecule is, however, lower than that of any one of the resonance structure. In other words, resonance hybrid is more stable than of any of the resonance structure. The difference in the actual energy and the lowest calculated energy of a resonance structure is called resonance stabilization energy or just resonance energy. Thus, resonance leads to stabilization of the actual molecules. 14.8. Identify the species that contain a conjugated system of pi bond. Explain your answer. CH2 double bond CH, CH2 CH double bond CH2. Part 1. CH2 double bond CH, CH double bond CH, CH3. Solution. 1 does not contain conjugated system of pi bond as the two C double bond C double bond are separated by 2 C single bond carbon carbon single bond. 2 contain a conjugated systems of pi bond as the two C double bond are separated by only one carbon carbon single bond. Rule to be followed for writing resonance structures. Resonance structures can be written only when all the atoms involved in the pi conjugated system lie in the same place, or the resonance structure must have the same number of unpaired electrons. Third point. Resonance structure contribute to resonance hybrid in accordance to their energy of stability. More stable, having low energy resonance structure contribute to large and thus are important. Thus, between the compared resonance structure, that resonance structure is more stable and therefore important, which has A. More number of covalent bond, B. More number of atoms with complete octet or duplet, C. Less separation if any of the opposite charge, D. Negative charge if any on more electronegative atom and positive charge if any on more electropositive atoms, and E. More dispersal of charge. 14.9. Write resonance structure of H, C double bond O minus and comment on their relative stability. First, the detailed bond structure of S, C double bond O minus showing all the valence electron is drawn, and then other resonance structure generated using curved arrow to show movement of pi electron. Two resonance structure written for HC double bond O minus H C double bond O minus give HCO minus double bond O. Both the resonance structure 1 and 2 are equivalent to each other and therefore equally stable. Identify the species which has a resonance stabilization. Justify your answer. Problem 14.10. Solutions. The bond structure showed that there is no pi bond, therefore no resonance and no resonance stabilization. CH3 and double bond O minus CH3 and O minus double bond O. N double bond O double bond is attached to O, which carry lone pair of electron in a p orbital. Therefore, resonance structure can be written on species is resonance stabilized. CH2 double bond CH single bond CH double bond CH2 give CH2 plus single bond CH double bond CH single bond CH2 minus. The Lewis structure show 2C double bond alternating with C single bond C single bond. Therefore, resonance structure can be written as shown and the species is resonance stabilized. Remember, when all the resonance structure of a species are equivalent to each other, the species is highly resonance stabilized. For example, RC double bond O CO3 2 minus. Problem 14.11. Write three resonance structure for CH3 CH double bond CH CHO. Indicate their relative stability and explain. CH3 CH double bond CH double bond OH give CH3 CH plus CH double bond CO minus H. QCH3CH minus CH double bond CO plus H. Stability order 1 is greater than 2, 2 is greater than T. First, 1 is more stable than 2, 2 is more stable than 3. First, the reason is C contain 1 contain more number of covalent bond. Each carbon atom and oxygen atom has complete octet and involve no separation of opposite charge. Therefore, the most stable resonance structure 2 contain one covalent bond less than in 1. One carbon C plus has only 6 valence electron. Involves suppression of opposite charge. The resonance structure 2 has negative charge on more electronegative O and positive charge on more electropositive carbon. It has intermediate stability. 2 contain one covalent bond less than in 1. Oxygen has only 6 valence electron. Involves suppression of opposite charge. Has negative charge on the more electropositive carbon and positive charge on more electronegative oxygen. All these factors are unfavorable for stability, therefore it is least stable. Resonance effect. The existence of resonance often results in developing polarities. In a molecule, the polarity produced in the molecule by the interaction between conjugated pi bonds or that between pi bond and p orbital on attached atom is called resonance effect or mesomeric effect. The effect is transmitted through a chain of conjugated pi bond. There are two types of resonance effect or mesomeric effect, designated as positive resonance effect plus R or plus M and negative resonance effect minus R or minus M. The positive resonance effect or electron donating or releasing resonance effect plus R effect. If the substituent groups has a lone pair of electron to donate to the attached pi bond or conjugated system of pi bond, the effect is called positive R effect, inductive effect. Groups such as OH, OR, O minus, NHR, halogen, etc. having lone pair of electrons show plus R effect. The plus R effect increase electron density at certain position in a molecule. Figure 14.11 show how the plus R effect in aniline increase the electron density at ortho and para positions. Plus R effect in aniline. Negative resonance effect or electron withdrawing resonance effect minus R effect. If the substituent group has a tendency to withdraw electron from the attached pi bond or conjugated system of pi bond towards itself, the effect is called minus R effect. Groups such as COH, CHO, CO, CN, NO2, COR, etc. show minus R effect. The minus R effect results in developing a positive polarity at certain position in a molecule. Show how minus R effect in a nitrobenzenes develop positive polarity at ortho and para positions. A minus R effect in aniline. N double bond O plus O minus. Minus R effect in aniline. Electromeric effect. This is temporary electronic effect exhibited by multiple bonded groups in the excited state in presence of a reagent. When a reagent approaches a multiple bond, the electron pair get completely shifted to one of the multiply bonded atoms, giving a charge separator structure. For example, our RC double bond O react with H plus as a reagent to give RC plus OH minus. This effect is temporary and disappear when the reagent is removed from the reactant system. Hyperconjugations. Hyperconjugations is a permanent electronic effect. Explains stability of a carbocation, free radicals or alkene. It is the localization of sigma electron of CH bond of an alkyl group directly attached to a carbon atom, which is part of an unsaturated system or has an empty p orbital or p orbital with an unpaired electrons. Species stabilized by hypoconjugations. Let us consider ethyl cation CH3CH2 plus. Here the positively charged carbon atoms with an empty p orbitals has an adjacent methyl groups, that is an alpha methyl groups. One of the CH bonds of this alpha methyl group is in alignment with the empty p orbital. The sigma electrons of this CH bond are delocalized into the empty p orbital and thereby stabilize the cations. Hyperconjugation in ethyl carbocation, empty p orbitals. Hyperconjugation is thus a sigma pi conjugations. The contributing structure 1, the contributing structure 2, 3 and 4 involving delocalization of an sigma electrons of CH bond show no covalent bond between carbon and one of the alpha hydrogen. Hyperconjugation is therefore called no bond resonance. More the number of such alpha hydrogen, that is hydrogen on the alpha carbon, more are no bond resonance structure and more is the stability. The relative stability of a carbon cation therefore decrease in the order CH3 C plus CH3 CH3 greater than CH3 CH plus CH3 greater than CH3 CH2 plus greater than CH3 plus. Let us now look at propene, which has methyl group attached to C double bond C. Delocalization of electron by hyperconjugation in propene can be depicted as shown. CH3 CH double bond CH2 CH double bond CH CH. Show the orbital diagram of hyperconjugation in propene. CH3 CH CH. Show the orbital diagram of hyperconjugation in propene. CH3 double bond CH CH minus CH3 CH CH minus. 14-15 show the orbital diagram of hyperconjugation in propene. The effect of hyperconjugation usually stronger than inductive effect. Basic principle of organic chemistry. Author Library Caltech Education 25034. Collect information about isomerisms.